Hello everyone, this is Donnell from Twig Learning Center, H2 A-Level Chemistry Specialist. Right, so we're going to go through the MCQ for alkylhalides from the 2020 prelim paper. So let's look at the first question. ACJC prelim. Okay, halothane is a general inhalation anesthetic used for the induction and maintenance of general anesthesia. Alright, which statement about halothane is correct? So you can see that halothane is actually a fluorochlorocarbon. Right, so fluorochlorocarbon tends to be inert, chemically stable, and non-flammable. So let's see which statement about halothane is correct. Okay, halothane is highly flammable. Nope, it's actually non-flammable. The molecule has two chiral center. In fact, the molecule only has one chiral center. Right, so there's a chiral center. There's actually a H over here. It may cause depletion of the ozone layer. That's true because UV rays can break the CCl bond. So the Cl radical that's being formed will convert the ozone to oxygen. So it depletes the ozone layer. So this is definitely correct. Okay, the IUPAC name is 1-bromo-2-chloro-111-trifluoroethane. Okay, actually the numbering is this. This carbon is numbered 1 and this number 2. So in fact, this molecule should be called 2-bromo, right? 2-bromo. The Br is on the second carbon. So 2-bromo, 2-chloro, 111-trifluoroethane. Okay, so the only error is over here. Okay, let's look at the next question. When bromomethyl benzene was heated with sodium hydroxide in dimethyl sulfoxide solvent, alright, the following reaction takes place. So you notice this is a nucleophilic substitution reaction because the Br was substituted with an OH. And they draw the energy profile diagram as shown. And you notice this is actually a single step, it's a one-step reaction. So for one step and nucleophilic sub, it's going to be SN2. So what is point X? Which of the following represents the species at point X? So point X is actually the transition state. So it works something like this. Br delta minus, C is delta plus, the polar bond. So the OH minus is a nucleophile, it'll attack the carbon, and it'll form this transition state product. So I'm going to just draw it out quickly. So the transition state will look something like this. Right. So the Br is starting to break, and the OH is starting to form. So this is the transition state. So this is at point X. So you look at the option, right? The best answer, of course, is only A. Okay, let's look at the next question. When this complete species is heated with ethanolic potassium hydroxide. So ethanolic potassium hydroxide with halogenate alkane, the mechanism is elimination. Okay, it's elimination. Which hydrocarbons could be produced? Okay, so if you have this compound, you could actually remove say Br from here and a H from here. Can you see that? So you form a double bond over here. So if you remove another Br and a H from here, you're gonna form another double bond. All right, another pi bond, which means in fact it should look something like this. So this is definitely one of the possible answer. So this carbon will now be a triple bond, all right, and you get a CH3. So this is in line with option number 1. Okay, so if you do another way, you could actually remove the H and the Br over here. So which means you have a double bond on both of these ends, right? So another product will be CH3, CH double bond here, and double bond here, all right? So, and the third part is this is the, let me see here. Yes, okay, so this double bond, and then this will be a CH3. Okay, so I have to draw a H over here. Right, so this is another possible product. And if you look at it carefully, this is option number 2. So there's no other ways to remove HBr. So actually 3 is incorrect. Okay, so the answer is 1 and 2, which means the option is B. Okay, let's look at the next question. Which sequence shows the correct order of decreasing ease of hydrolysis? So hydrolysis essentially is like, for example, hydrolysis, you can take it as water, delta minus, delta plus. Water is the nucleophile. It's going to attack the carbon and kick out the Cl. All right, so it's going to substitute the Cl with probably an OH in the presence of water. Okay, so this is actually hydrolysis. So the rate of hydrolysis is only dependent on the bond energy of the carbon halogen bond. So this CCl bond is the strongest, right? Followed by CBr, then followed by Ci. So in terms of reactivity, right, it takes more energy to break the CCl bond. So the chloro alkane will be the slowest because it takes a lot of energy to break the CCl bond. So it'll be, the reactivity will go this way. All right. And something you also can take note of for halogenoarene, they are kind of unreactive, right? This one's actually unreactive. The reason is because the lone pair in the p orbital of Cl can delocalize into the benzene ring. All right. So once it can delocalize, it gives it what they call partial double bond character. So the CCl bond is kind of strong. Okay, it's actually strengthened by this delocalization. Right, we call it partial double bond character. So it'll be very hard to undergo hydrolysis. So let's look at the option. Okay, the answer for this question is probably D, right? Okay, why? You can see that this is the least reactive because it's partial double bond character. And actually this is the most reactive because the C-Br bond, this is considered halogenoalkane. This is only this one is the halogenoarene, right? Because the Cl is directly attached to benzene ring, but this Br is not directly attached to benzene ring. So this is this one here is actually considered a halogenoalkane. Halogenoalkane, not arene. So this is going to be the most reactive compared to the second one because the C-Br bond is easier to break compared to the CCl bond. So being easier to break, it will be the fastest, right? So that's why the option is D. Okay, let's look at question 5. Right, if you look at this energy profile diagram, you notice it's actually 2 steps. So if there are 2 steps, it means that it's probably SN1, right? SN1. Okay, so which of them shows a SN1 mechanism? So normally tertiary halogenoalkane favors SN1, and primary will favor SN2. Okay, favor SN1 because it forms a stable tertiary carbocation. Okay, for primary it favors SN2 because there's actually less steric hindrance. Right, less steric hindrance. Okay, so let's look at the different halogenoalkane. This is actually a tertiary halogenoalkane. This is a primary halogenoalkane, and this is also a primary halogenoalkane. So which of the following can be represented by the above diagram? So it looks as if you're only having the first one, right? Because it's a tertiary halogenoalkane. So tertiary halogenoalkane will undergo SN1, and this is a 2-step in SN1, so the answer has to be D. Okay, let's look at the next question. Right, when sodium iodide in propanone is added to an optically active sample of 2-bromobutane, so optically active means it has a chiral center, right? So the chiral center is over here. Sodium bromide precipitate is formed. All right. So in fact, this, if you look at the reaction, it's actually a nucleophilic substitution reaction, and you can see that the Br was substituted with I. All right, and the iodine or the iodide was actually the nucleophile, right? And this is actually a second order reaction, which means that this reaction is SN2. All right, it's SN2. Second order is SN2. So which means you have compound like this, SN2. So I put a CH3, right? CH2, CH3, right? So the nucleophile in this case is I minus, will be attacking this carbon that has a partial positive charge, right? This is the SN2 mechanism. Okay, so part A, a racemic mixture is formed. This is wrong. A racemic mixture is formed only if it undergoes SN1, right? Not SN2. Okay, the reaction is bimolecular. Okay, bimolecular. This is true. Bimolecular means it's an SN2 reaction. There are actually 2 reactants in the slow step. All right, so that's why it's called bimolecular. All right, so this actually is true. The reaction involves nucleophilic sub. Yep, I minus was the nucleophile. Substituted the Br. Okay, the Br will actually leave. Okay, that's true. A similar experiment using 1-bromobutane. Okay, if you look at this compound, this is a secondary alkyl halide. Okay, alkyl halide, secondary. All right. But now when I ask you to draw 1-bromobutane, 1, 2, 3, 4, 1-bromobutane, this is actually a primary alkyl halide. Okay, so a primary alkyl halide actually is if it undergoes SN2, is actually going to be a faster rate of reaction because there's less steric hindrance. Okay, this one has 2. You can see there are 2 bulky alkyl groups. But if you look at this compound, it probably looks something like this, right? There's a H here, there's a H here, and there's only one, two, three, four. Okay, there's only one bulky alkyl group, right? So which means the nucleophile I minus will be able to attack the carbon more easily, right? So it'll be a faster rate reaction, and you will produce a PPT in a lesser amount of time. So since secondary is after 10 minutes, this will take less than 10 minutes, right? So the answer, this is actually a correct statement, right? So which means the question is asking for which is incorrect, has to be A. Okay, let's look at the next question, question 7. Okay, I'm just gonna draw for you what is happening. So for this question, the answer is actually A. So the first step, bromine, right? Bromine and alkene. This reaction is electrophilic addition. So I'm going to just draw Y. So Y looks like this. Okay, it undergoes addition, electrophilic addition. This is your structure for Y. Okay, after that, it undergoes, they add ethanolic KCN and heat. This is nucleophilic sub. Alright, which means you actually kick out the Br and replace with a Cn, kick out the other Br and replace with a Cn. So Cn minus was the nucleophile. And the last step, the Cn, right? The Cn undergoes reduction. So it becomes an amine. So it becomes CH2NH2 and CH2NH2, right? So that's why the answer is A. Okay, let's look at the next one. Question 8. Okay, when methylamine is heated with excess chloromethane. So when you have nucleophile like this, and then which is an amine and heated with excess chloromethane, you must understand that this reaction undergo multi-substitution, right? Multi-sub, all right? So what is the final product and the white solid that is very soluble? So very soluble, and it's a white solid. This is actually ionic, all right? This compound is actually ionic. So let's see how it works. Delta minus, delta plus, the lone pair on N attack the carbon, right? What happens is the Cl will leave and you have to kick out a H, right? So this is the next product, right? Plus HCl. Okay, maybe put plus HCl over here, right? So because you have excess halogen alkane, right? So you have excess, you have excess chloromethane, right? So delta minus, delta plus, same concept happens. Attack the carbon, right? And then kick out the Cl and kick out another H. This is your next product, right? So N, CH3, 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 and plus HCl. And actually, it will undergo one last nucleophilic substitution, all right? But in this case, there's no more hydrogen to be kicked out from the N. So it works this way. Lone pair attack the carbon. You just kick out the Cl, right? So the final product is essentially N, CH3, 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 as this is a positive cation, all right? And there's a Cl minus. So you try to calculate the entire MR, okay, of this compound. It will be C, all right? And it's definitely very soluble in water because it's an ionic compound here. Okay, let's look at question 9. Right, the first one is actually mal-oxidation. What you're going to get is a diol. So let me just draw it out. Okay, let's draw it out. So you get diol means OH and OH. Okay, the second one is strong oxidation. You get benzoic acid. Third one is nucleophilic substitution. The ammonia is the nucleophile. It will replace the Cl with NH2. And the last one is also nucleophilic substitution. The Cl will be replaced with Cn. So if you're going to calculate, they want for the largest change in the MR. So for the first one, I'm just going to add the 2O and the 2 H's. Can you see that? I added 2 hydrogen and the MR of 2 oxygen, right? 16 plus 16 is 32. So you notice the change is 34. For the second one, you are taking away, you have 5 H, but there's 1 H. You're taking away 4 H's and you're adding 2O. So you took away 4 H's and added 2 oxygen. The overall change is plus 28. Okay, for C, right, you are actually is undergoing nucleophilic sub and you replace the Cl with NH2. So you take away 35.5 and then you plus 16 NH2. 14 plus 2 is 16. So the overall change is minus 19.5. For the last one, you took away the Cl nucleophilic sub, replaced with the nucleophile Cn, right? So I'm gonna just take away 35.5 plus carbon, which is 12, plus nitrogen, which is 14, is 26. So you get a minus 28. So you can see that the biggest change is actually over here. So plus 34, that's the largest change. So the answer has to be A. Okay, let's look at question 10. Which compounds on heating with ethanolic sodium hydroxide produce only one product? Okay, and you can see that the final formula doesn't have any more Br. And this mechanism is actually elimination. So over here, you're going to remove the H and the Br. Alright, the H and Br from here, you get the double bond. Okay, and you can actually remove the H and the Br from here. So you get a double bond here. At the same time, I'll say that you could actually also remove the H and the Br from here, which means you're going to get this compound, right? But actually they are the same, right? If you rotate 180 degrees, right, they are actually the same thing, right? So the question is only asking to produce one product, but this one actually produces one product since they're the same. Okay, so one is definitely correct. Okay, for the second one, I'm just going to take away the Br and the H from here, same thing. All right, and I will remove the Br and the H from here. Okay, so which means I'll get this product. Right, so there's no other way to take away the Br and the H, no other way for elimination to take place. So this is also only one product. Okay, for the last one, you can take away the Br and the H from here. So again, you get the double bond. All right, but for the other side, you could actually take away the Br and the H from here. So which means you could actually get a double bond on this end. You could also take away the Br. Let me just erase this. So you could also take away the Br and the H from here. Right, so the double bond could be here. So this one will give you two possible products, right? So only 1 and 2 seems to be the right answer. Okay, let's look at question number 11. Okay, when a substance X is shaken with aqueous silver nitrate at room temperature, there's no immediate PPT. Okay, you need to take note that all the acyl chloride, like B and D, right? When you have acyl chloride, okay, acyl chloride are highly reactive. So in the presence of water, because this is the aqueous medium, right? So in the presence of water, it will form RCOOH. It will undergo hydrolysis to form RCOH and HCl. Right, so the Cl minus is being kicked out, so the Cl minus will immediately react with Ag plus, and you see a white PPT of silver chloride. So since the question says there is no immediate white PPT, it means it mustn't be any of the acyl chloride. And if you look at the next two, all right, they say when X is bought with sodium hydroxide and then as co-acidified with nitric acid, and then you added silver nitrate, this is when a white PPT forms. So it means that this must be an alkyl halide, okay? Not aryl halide, okay? So you can see from here, this one actually is chlorobenzene. It has partial double bond character. All right, we know that the lone pair here can delocalize. It strengthens the bond. So we add OH minus as a nucleophile. All right, it tries to attack this carbon. All right, try to attack this carbon to break this CCl bond, but it's unable to. Right, so there's no substitution of the Cl minus. Hence, you won't get any PPT. So the only PPT that can be formed is with alkyl halide. So this the Cl minus will be kicked out. Right, so the answer is definitely A. Okay, let's look at question 11. What's the total number of hydrocarbons formed, including stereoisomers, when 2-chlorobutane is heated under reflux with ethanolic NaOH? So when you see ethanolic NaOH, you must think of elimination. Okay, elimination. So I'm going to draw 2-chlorobutane. So this is what it should look like. 2-chlorobutane. So the Cl is over here. All right. So if undergo elimination, you would remove, say, the H from here. Let me just draw the H over here. You remove the H and the Cl from here. All right, and you form a double bond over here. All right. So you could actually form a trans or a cis molecule, right? So the cis and trans. So the other possibility, so that's where the double bond is, right? Okay. So what's the other possibility? The other possibility is, let me just draw it out first. All right. The other possibility is you're removing the H from here and the Cl from here. So this is where you remove your HCl. So the double bond will be formed over here. right? If that's the case, this is your molecule, and this if you can see from here, this molecule doesn't have cis trans, so actually altogether there will be 3, right? So the answer will be C. Okay, let's look at the next question. Question 13. Ethanolic silver nitrate is added to a sample of halogen alkane, and the following reaction takes place. So you can see that this was the nucleophile, right? In fact, I'm just going to draw it here very quickly. This guy was the nucleophile, all right? Maybe I should just show it this way. So you can take it as R is the carbon is delta plus, X is delta minus, the lone pair O actually attacks this carbon and kick out the X, so you get this compound here. All right, and then once you have the X minus that is being substituted, it will combine with Ag plus, right, and you form the silver halide. Okay, so the rate of such reaction for halogen-alkane, you just have to remember that the rate of reaction is only dependent on the strength of the CX bond. So you can see that with 2-bromobutane and 2-chlorobutane, CBr bond is actually weaker, and CCl bond is actually stronger. All right, because Br is actually bigger than Cl, so the longer the bond length, the weaker the bond, All right, the shorter the bond length, the stronger the bond. So you can see that it takes a faster rate, all right, only 10 seconds for the silver bromide PPT to form. This is silver bromide. Okay, and of course this is silver chloride. Okay, so it takes a shorter period of time for the silver bromide to form because the CBr bond is actually broken more easily over here. All right, so when you have Rx, yeah, the CBr bond is broken more easily, faster rate of reaction. So which means the answer will be B. Right, the Br atom is actually larger than Cl atom, so Cl bond is weaker than CCl bond. Okay, let's look at question number 14. Right, okay, these are the reactions. They show the epoxy resins, and they say one monomer used in their manufacture has the following structure. Right, the monomer is manufactured in this manner. Right, they say which of the statements are correct in the above synthesis. Okay, so from the first stage 1, you notice that this is an alkane. So the H was kicked out or substituted with a Cl. This is free radical substitution. All right, under probably with UV light. Okay, so stage 1 requires the use of UV light. Yes, it's true. The UV light is supposed to break the Cl bond, right, in the initiation step. Okay, it's supposed to break this bond in the initiation step. Okay, once you get a Cl radical, it will react with the alkane. Okay, look at stage 2. Stage 2, what is happening is you're adding a Cl and an OH across the double bond, right? So this is an alkene, so alkene undergo electrophilic addition, right? Electrophilic addition, so stage 2 is also correct. Okay, look at stage 3. Stage 3 shows this product. So what happens, actually, I'll draw it up. So when sodium reacts with the alcohol, what you end up getting is actually O minus. So you can see that this is delta minus and this is delta plus. So the O will actually attack this carbon, all right, and the Cl will be substituted. And this is the product actually. So you get the O joined to this carbon, all right, and then you have this and the Cl over here, all right. So this is your final product. Okay, this is your final product, and the mechanism, of course, is nucleophilic substitution, right? So stage 3 is also correct, which means the answer is A, right? 1, 2, 3. Okay, let's look at next question. Alkane and sodium react when heated under reflux in an inert organic solvent to form an alkane according to the reaction. When a mixture of equal number moles of 2 different alkanes are used, which of the following alkanes will not be formed? Okay, so you can see that the two alkane, right? You just take the R group, right, the alkyl group, and they combine with each other, right? They combine each other. So you could actually do this, right? So the alkyl group is either CH3, CH2, or the alkyl group is this one here. Maybe I should draw it out. CH3, CH, H, and sorry, this is I. Sorry, okay, this is I. All right, and this is a CH3. Okay, so let's see what are the possible structures that you can get. So I'm gonna just draw it this way. Okay, let's look at the R group. This is R group over here, and the R group for the other one is just CH3, CH2I, but the R group you're looking at is this one. Okay, so I'm going to call this R1, I'm going to call this R2. So the three possibilities: you can get R1, or you could get R2, or you can get R1 joining with R2. Right, so let's look at the possibilities. So if you look at the first one, I'm going to just draw A and look at A, right? A looks like that. CH3, CH, CH3, CH, CH3, and CH3, right? So in fact, this is actually R1. If you notice, R1. Okay, let's look at, Okay, let's look at the next one. Okay, let's look at the next one. If you look at the next one, I'm going to just draw it out so hopefully you can see. This is CH3, CH2, CH, CH3, CH3. Okay, you look at this part, so I'm going to just divide it. If you look at it carefully, this is actually R2, R1. All right, so that's B. Okay, this is B. Okay, let's look at C. C, hopefully you can see more clearly. This actually, here and here is actually R2, R2. All right, so you have R1, R1, R2, R1, and R2, R2, and this is not possible at all. Okay, so which means the answer is D. Okay, let's look at the next one. All right, let's do the next one. Byproducts are formed during the preparation of many organic compounds. This usually occurs because the reagents can react in more than one way. All right, so in this reaction, in fact, it is nucleophilic substitution, right? OH minus actually attack the carbon over here because it's delta minus delta plus, and probably kicked out the Br. So this is nucleophilic sub, where OH minus is the nucleophile. Okay, which could be a byproduct of this reaction? Okay, actually there's another reaction when involves sodium hydroxide, but technically it should be ethanolic NaOH. Okay, when you have ethanolic NaOH, actually you will end up getting alkene. And actually the mechanism is elimination, right? So this is possible as a byproduct, even though they didn't say ethanolic. So if I remove the Br and the H from here, you realize that you could possibly get an alkene. So this is the possible answer, right? They say what could be a byproduct. So this is definitely going to be a possible answer. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.